Today, for the introduction, I thought we can watch parts of a video together. This will be an introduction to this course. This is one of my favorite videos on PBS, Prediction by Numbers on NOVA. I thought to watch this together and get familiar with some of mathematical and statistical concepts that we are going to talk about this semester. I thought by watching this video, you will better understand the importance of statistical, mathematical, and computational analysis. Before I forget, actually, since I plan to show you some parts and discuss them, I may pause the recording, so for this reason, this video may seem edited. Okay, don't forget, like always, I'm going to ask you some questions while you are watching, so remember to have a pen and paper with you. By the way, I realized the last video I recorded had this awful background noise, which was kind of caused by my computer's CPU. My laptop couldn't handle all these multiple apps together. They were working all together and then creating this kind of sound background noise. Okay, so sorry about that. Okay, so now let's watch this together.
The Orange County Fair, held in Southern California. In theory, these crowds hold a predictive power that can have startling accuracy. But it doesn't belong to any individual, only the group. And even then, it has to be viewed through the lens of mathematics. The theory is known as the wisdom of crowds, a phenomenon first documented about 100 years ago. Statistician Talithia Williams is here to see if the theory checks out, and to spend some time with the fair's most beloved animal, Patches, a 14-year-old ox.
It was a fair kind of like this one, where in 1906, Sir Francis Galton came across a contest where you had to guess the weight of an ox. Like Patches you see here behind me.
After the ox weight-guessing contest was over, Galton took all the entries home and analyzed them statistically. To his surprise, while none of the individual guesses were correct, the average of all the guesses was off by less than 1%. That's the wisdom of crowds. But is it still true?
So here's how I think we can test that today. What if we ask a random sample of people here at the fair if they can guess how many jelly beans they think are in the jar? And then we take those numbers and average them and see if that's actually close to the true number of jelly beans. Guess how many jelly beans are in here? Come on, guys. Everybody's got to have their guess. I see your mind churning.
1227. 846. Probably like 925.
There you go. So just write your number down. There you go.
The 135 guesses gathered from the crowd vary wildly.
The range of our guesses was from the smallest was 183. The largest was 12,000. So you can tell folks were really guessing. But when we take the average of our guesses, we get 1,522. So the question is, how close is our average to the actual number of jelly beans? Well, now's the moment of truth. All right, so the real number of jelly beans was 1,676. The average of our guesses was off by less than 10%. So there actually was some wisdom in our crowd.
Though off by about 10%, the average of the crowd's estimates was still more accurate than the vast majority of the individual guesses. Even so, the wisdom of crowds does have limits. It can be easily undermined by outside influences and tends to work best on questions with clear answers, like a number. The steps Talithia took reflect a process going on all around us these days in the work of statisticians.
Thanks, everybody. So we collected this data, right? We analyzed it mathematically, and we got an estimate. It was pretty close to the actual true value. That's math and statistics at work.
Okay, so wisdom of crowd, which refers to the idea that a large group of people are collectively smarter than individual experts. For crowd actually to be wise, they must be characterized by diversity of opinion, and each person's opinion must be independent of those around him or her. Okay, so I thought to talk about the law of large number here as well. And in my opinion, if they increase the number of people who answered, who gave their guesses, if they increase that number, they would have more accurate result and wouldn't be off by less than 10%, maybe it would be off by less than 5% or 1% if they increase their sample size. So now I wrote down their sample size, the number of people who guessed was 135. Imagine if they increase this number to 1,000, so what would happen? And this is actually something in future I'm going to talk about. Let's watch the rest of this video.
Why I love statistics is that it predicts the likelihood of future occurrences, which really means it's the best crystal ball that humankind can have.
Ultimately, all the predictive power of statistics rests on a revolutionary insight from about 500 years ago. That chance itself can be tamed through the mathematics of probability. Viva Las Vegas. Here's a city full of palaces built on understanding probability and fueled by gambling. Which may seem a funny place to find mathematician Keith Devlin. But mathematics and gambling have been tied together for centuries. Today in a casino, you'll find roulette, slot machines, blackjack. Playing craps is also known as rolling the bones, which is more accurate than you might think.
Humans have been gambling since the beginnings of modern civilization. The ancient Greeks, the ancient Egyptians would use the ankle bones of sheep as a form of early dice.
Surprisingly, while the Greeks laid the foundation for our mathematics, they didn't spend any effort trying to analyze games of chance.
It seems to have never occurred to them, or indeed to anybody way up until the 15th, 16th century, that you could apply mathematics to calculate the way these games would come out.
16th century Italian mathematician Girolamo Cardano made a key early observation. That the more times a game of chance is played, the better mathematical probability predicts the outcome, later proven as the law of large numbers. Examples of the law of large numbers at work surround us.
When I flip this coin, we have no way of knowing whether it's going to come up heads or tails. That time it was heads. On the other hand, if I were to toss a coin 100 times, roughly 50% of the time it would come up heads, and 50% of the time it would come up tails. We can't predict a single toss, we can predict the aggregate behaviour over 100 tosses. That's the law of large numbers.
In fact, casinos are a testament to the iron hand of the law of large numbers. The games are designed to give the casinos a slight edge over the gambler. Take American roulette. On the wheel are the numbers 1 through 36, half red and half black. Betting $1 on one color or the other seems like a 50-50 proposition. But the wheel also has 2 green slots with zeros. If the ball lands in those, the casino wins all the bets on either red or black. And that's the kind of edge that makes the casino money over the long run.
Customers are gambling. The casino is absolutely not gambling, because they may lose money, they may lose a lot of money to 1 or 2 players, but if you have thousands and thousands of players, by the law of large numbers, you are guaranteed to make money.
The law of large numbers comes into play outside of gambling, too. In basketball, a field goal or shooting percentage is the number of baskets made divided by the number of shots taken. But early in the season, when it's based on a low number of attempts, that percentage can be misleading.
At the beginning of the season, a less skilled player might get off a few lucky shots in a row. And at that point, they'd have a super high shooting percentage.
Meanwhile, a very skilled player might miss a few at the beginning of the season and have a low shooting percentage. But as the season goes on and the total number of shots climbs, their shooting percentages will soon reflect their true skill level. That's the law of large numbers at work. A small sample, like just a few shots, can be deceptive, while a large sample, like a lot of shots, gives you a better picture. The gambling observations that led to the law of large numbers were a start. But what really launched probability theory and opened up a door to a whole new way of thinking about the future was a series of letters exchanged between 2 French mathematicians, Blaise Pascal and Pierre de Fermat, in the 1650s, about another gambling problem that had been kicking around for a few centuries. A simplified version of the problem goes like this. 2 players, let's call them Blaise and Pierre, are flipping a coin. Blaise has chosen heads and Pierre tails. The game is the best of 5 flips, and each has put money into the pot. They flip the coin 3 times, and Blaise is ahead 2-1. But then the game is interrupted. What is the fair way to split the pot?
The question is, how do they divide up the pot so that it's fair to what might have happened if they'd been able to complete the game?
Fermat suggested imagining the possible future outcomes if the game had continued. There are just 2 more coin flips, creating 4 possible combinations: heads, 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 tails, tails, heads, and tails, tails. In the first 3, Blaise wins with enough heads. Pierre only wins in the last case. So Fermat suggested that a 3-1 split was the correct solution. The key breakthrough was imagining the future mathematically, something even Pascal had trouble with.
Because what Fermat did was say, let's look into the future, look at possible futures, and we'll count the way things could have happened in different possible futures. It was a simple arithmetic issue, but the idea of counting things in the future was just completely new, and Pascal couldn't wrap his mind around it.
Eventually, Pascal accepted Fermat's solution, as did others. And today, that exchange of letters is regarded as the birth of modern probability theory.
People realized the future wasn't blank. You didn't know exactly what was going to happen, but you could calculate with great precision what the likelihood of things happening were. You could make all of the predictions we make today and take for granted, you could make them using mathematics.
It was a fundamental insight and one of the doors that led to the modern world. Inherent in all our attempts to predict the future, from the stock market to insurance to web retailers trying to figure out what you might buy next, is the idea that with the right data, the likelihood of future events can be calculated.
Okay, so what we learned here is about law of large number and randomness. So there are some definition I thought you should know. Statistical inference. Statistical inference uses sample data to draw conclusion about the entire population. And now, what is sample itself? Sample is a small part of population. Well, a good sample must be chosen randomly. And there are some concepts in sample and population we will talk about later, like a statistic, parameter, all of these I'm going to talk about that later. The law of large number itself. So when we perform an experiment over and over for a long trial, for a large number of trial, we will reach the information of population easier. So for example, we will reach the average of population. We will get closer and closer to the average of population. Now there is another version of law of large number. We call that central limit theorem. We talk about that also, but I just want you to get familiar with these concepts. Law of large number, central limit theorem. These are all telling you we can use the information of sample, increasing the sample size and get closer to the information of population. Okay, so randomness and probability itself. We call a phenomenon random if individual outcomes are uncertain, but there is a kind of nonetheless or a regular kind of distribution of outcomes in a large number of repetition. So that's the reason experiments, if they are doing experiments in lab, they must do that over and over to increase the number of experiment, to increase the number of repetition, to decrease the bias or kind of error. So the probability of any outcome of a random phenomenon is the proportion of times the outcome would occur in a very long series of repetition. Okay, so the law of large number in action would be actual, or in parentheses, observed probability approaches the theoretical or kind of expected probability. Okay, I wanted to bring this picture to show you this figure, which is about law of large number of throwing tosses toss a coin. So the figure shows the result of two trials. One is black, one is red, of 5,000 tosses each. The proportion of tosses of a coin that give a head changes as we make more tosses. If you see, it's approaching 0.5, which is the probability of observing head. Eventually, however, the proportion approaches 0.5, which is, as I mentioned, the probability of head. So what it says, it's talking about the law of large number, the long series of trial, large number of trial will make it possible for you to have a correct prediction. Let's watch the rest.
In fact, the scientific method demands a hypothesis which leads to a prediction of results from a carefully designed experiment that will test its claim. Surprisingly, it wasn't until the 1920s and 30s that a British scientist, Ronald A. Fisher, laid out guidelines for designing experiments, using statistics and probability as a way of judging results. As an example, he told the story of a lady who claimed to taste the difference between milk poured into her tea and tea poured into her milk. considered ways to test that. What if he presented her with just one cup to identify?
If she got it right one time, you'd probably, well, yeah, but she had a 50-50 chance just by guessing of getting it right. So you'd be pretty unconvinced that she has the skill.
Fisher proposed that a reasonable test of her ability would be 8 cups, 4 with milk into tea, 4 with tea into milk, each presented randomly. The lady then had to separate them back into the 2 groups. Why 8? Because that produced 70 possible combinations of the cups, but only 1 with them separated correctly. If she got it right, that wouldn't prove she had a special ability. But Fisher could conclude, if she was just guessing, it was an extremely unlikely result, a probability of just 1.4%. Thanks mainly to Fisher, that idea became enshrined in experimental science as the p-value, p for probability. If you assume your results were just due to chance, that what you were testing had no effect, what's the probability you would see those results or something even more rare?
If you assume that there's a process that is completely random and you find that it's pretty unlikely to get your data, then you might be suspicious that something is happening. You might conclude, in fact, that it's not a random process, that this is interesting to look at what else might be going on, and it passes some kind of sniff test.
Fisher also suggested a benchmark. Only experimental results where the p-value was under 0.05, a probability of less than 5%, were worth a second look. In other words, if you assume your results were just due to chance, you'd see them less than 1 time out of 20. Not very likely. He called those results statistically significant.
Statistically significant. Now, this is a terrible word. It could be quite insignificant. You could be detecting a very, very, very small effect, but it would be called, in the mathematical lingo, significant.
Okay, so this is very funny, p-value, concept of p-value, because later, if I have a chance, I'm going to go through Bayesian theorem, which is a kind of modern way of looking at significance, the result being significance. So when they say a p-value less than 0.05, this is the alpha, level of significance, 0.05. It can be 0.01, it can be different values, and these are all by choice. Whose choice? The person who is kind of doing this experiment, right? And then in most of scientific papers that you are going to submit to a journal, you are trying your best to have a result that is significant at 0.05 significance level, or p-value less than or equal to 0.05. Why? I mean, that doesn't make sense. And I actually heard about this, that if in a journal your p-value of the experiment is not less than 0.05, means it's not significant, they are not going to accept your paper because there's no interesting result to offer and publish. And this 0.05 is actually very important. If it is maybe 0.01, some journals don't accept that because some specific journals just say 0.05. And this is what we want. This is what we want to see and publish in our journal. So this is a kind of interesting concept. We are going to review all of them if you have a chance during the course, and we talk about all of them and have some project based on this. Let's watch this.
The presidential election of 2016 was a tough one for pollsters, the folks who conduct and analyze opinion polls. Hillary Clinton was the overwhelming favorite to beat Donald Trump right up to Election Day.
Trump is headed for a historic defeat.
He's going to lose by a landslide.
I think that she's going to have a very good night.
The New York Times put Trump's chances at 15%. One pollster on election night gave him 1%.
A projection of a 99% chance of winning, is that correct?
The odds are overwhelming of a Hillary Clinton victory on Tuesday. I would be very surprised if anything else happened.
And of course, Trump won, and Clinton lost.
People were repeatedly told Hillary Clinton is the candidate most likely to win this election, and she didn't. And I think that really left people feeling almost lied to, almost cheated by these numbers.
So what was going on with the polls? And exactly how do people predict elections? One way is just by asking people who they'll vote for.
One of the great things about polling is that we don't have to talk to everybody in order to find out what the opinions are of everybody. We can actually select something called a sample.
Sampling is a familiar idea. To see if the soup is right, you taste a teaspoon, not the whole pot. To test your blood at the doctor, they typically draw less than an ounce. They don't drain you dry. But in many circumstances, finding a representative sample is harder than it sounds.
Let's suppose that this is the population of about 1,000 people in a city. And we want to know, are people for or against converting a park into a dog park? And so these green beads down here are going to represent people who are for it, and the red beads are folks who are against it.
Talithia's first step is to take advantage of an unlikely ally in sampling: randomness.
The beauty of randomization is that as long as you throw everything from your population into one pot and randomly pull it out, you can be sure that you're within a certain percentage points of the actual value that's in that pot.
So the plan is to randomly sample the beads. But how many? That depends on how much accuracy Talithia wants. One measure is the margin of error. The maximum amount the result from the sample can be expected to differ from that of the whole population. It's the plus or minus figure, often a percentage, you see in the fine print in polls. But there's also confidence level. Inherently, there is uncertainty that any sample really represents a whole population. The confidence level tells you how sure you can be about your result. A 90% confidence level means, on average, if you ran your poll or sample 100 times, 90 of those times it would be accurate, within the margin of error. Talithia knows the total number of beads is 1,000, and she's settled on a plus or minus 5% margin of error at a 90% confidence level. That means she needs a sample size of at least 214 beads.
Here are the results. We got 103 red beads and 111 green. So about 48% of our population would vote against, and about 52% would vote for. Now, remember that margin of error that we talked about, that plus or minus 5%? So once you take that into account, those numbers really aren't that different at all. So I guess you could say this puppy is too close to call.
In fact, within the margin of error, the stats got it right. There were an equal number of red and green beads in the jar. While the sampling error built in from the mathematics can be quantified, there are other errors that can't.
The other parts of the error, how we word our questions, how the respondents feel that day, the responsibility to predict what their behavior is going to be somewhere down the line. All those sources of error are something that we can't calculate.
And there's a catch to random sampling for polls, too. A few decades back, when just about every household had a landline, finding a random sample meant randomly dialing phone numbers.
Into the 1970s and the 1980s, we were getting 90% response rates. If we randomly chose a phone number, somebody on the other end of that phone would pick it up and would do the interview with us.
Those days are over. Thanks to caller ID and answering machines, people often don't answer their landlines anymore, if they even have one. response rates are way down.
Only about 10% of people respond to polls. So you're kind of crossing your fingers and hoping the people you reach are the same as the ones that are actually going to vote. For example, we found in 2016, pollsters were not reaching enough white voters without college degrees.
If there's a bias in the data, you cannot recover from it, as we've seen from some recent elections.
After Donald Trump's surprise win, many wondered if polling was broken. But if you look at the polls themselves and not the headlines, on average, polls on the national and state level were off by historically typical amounts.
So when I hear people say, oh, the polls were wrong, then it probably reflects people's interpretations about the polls being wrong, where people, for various reasons, looked at the polls and they said, these numbers prove to me that Clinton's going to win. When we looked at the polls, we said, these numbers certainly make her a favorite, but they point toward an election that's fairly close and quite uncertain, actually.
And in 2016, the U.S. presidential election was just that close. Trump's victory depended on fewer votes than the seating capacity of some college football stadiums, spread across 3 states: Pennsylvania, Wisconsin, and Michigan. And there were some problems with the polls in those states that led to underestimating Trump's support, according to a postmortem by a consortium of pollsters. Nate Silver, the founder of the website 538, is one of the biggest names in polling, even though he doesn't generally conduct polls.
Our job is to take other people's polls and to translate that in terms of the probability, to say basically whether who's ahead, which is usually pretty easy to tell, but then how certain or uncertain is the election is the more difficult part.
Like a meteorologist, Nate presents his predictions as probabilities. On the morning of Election Day 2016, he gave Clinton about a 70% chance of winning, and Trump about a 30% chance. That's like rolling a 10-sided die with 7 sides that are Clinton and 3 that are Trump.
People who make probabilistic forecasts, they're not saying that politics is intrinsically random. They're saying that we have imperfect knowledge of it, and that if you think you can be more certain than that, you're probably fooling yourself based on how accurate polls and other types of political data are.
Ultimately, interpreting a probability depends on the situation. While a 30% chance might seem slim, if you learned the flight you were about to board crashed 3 out of every 10 trips, would you get on the plane?
As this plane only makes it to its destination 7 out of 10 times, please pay attention to our short safety briefing.
Or if a weather forecast...
Well, that was the most kind of funniest part, the flight part. Yeah, if you know how many times a flight will crash, are you going to still use airplane? Okay, so there were some important concepts here. They explained, they talked about, like confidence interval, margin of error. We are going to have some example of them. I mean, this was amazing. I think they explained it very well, and we are going to work on them more. One thing about margin of error that they were showing, and they kind of calculated the sample size based on the margin of error. So there's a kind of formula for margin of error. Margin of error is equal to z multiply sigma standard deviation divided by square root of n, which is sample size. And the z is also the kind of test statistic which is related to the confidence interval they were talking about. These are some statistical concepts that you may learn in basic statistics. So if they had a kind of larger margin of error. Based on this formula, the margin of error has kind of inverse direction to the sample size, because the sample size is in the kind of denominator of this equation of margin of error. So if they have a higher margin of error, they will have a smaller sample size. And imagine the sample size I was explaining is under square root, and it will be way kind of a smaller. If they had a kind of a smaller margin of error, they will have a larger sample size. So what happens if they increase the sample size, in parentheses, if we have a constant confidence interval and the rest of things in the equation, if they increase the sample size, the margin of error will decrease. So these are also something that we are going to talk about later, and we are going to look into all of this in more detail in the future. Okay, let's watch the last part.
Good morning, Coast Guard Sector Boston Command Center. Mr. Fleming speaking.
Good morning, sir. A caller reports that a friend went paddleboarding earlier in the morning, but he's now overdue. The Coast Guard initiates a search with a 45-foot response boat.
Engaging.
Out of Boston Harbor.
Coming out.
Unfortunately, a paddle craft in trouble has grown increasingly common.
You are required to have a life jacket on. Reason for that is in 2015, I think we had 625 deaths nationwide. A number of those people that were recovered without a life jacket.
The command center also launches another boat out of Station Point Allerton in Hull.
Your time disconnected! Stand clear, wise.
The caller said the missing person typically paddled between Nantasket Beach and Boston Light, about 3 miles away. But with all the unknowns, where he got into trouble and how he may have drifted, the search area could be as large as 20 square miles. Search and rescue operations are often based on unique circumstances and require action despite incomplete information. To attack problems like that, statisticians turn to an idea that originates with an 18th century English clergyman interested in probability, Thomas Bayes. Imagine you're given a coin to flip and you want to know if it is fair, 50-50 heads or tails, or weighted, to land more on heads than tails. The traditional approach in statistics and science doesn't assume either answer and uses experiments to find out. In this case, that involves flipping the coin, a lot. Or you could approach the problem like a Bayesian. Unlike traditional statistics, that means starting with an initial probability based on what you know. In this case, all the coins you've ever come across in a lifetime of flipping coins have been fair. Seems likely this one is probably fair too. Next, you also flip the coin, updating the probability as you go. Let's say it starts off with several heads in a row. That might make you wonder, increasing your probability estimate that it's weighted. But as you flip it more times, those start to look like chance. In the end, your best estimate is that it is probably a fair coin, but you are open to any new information, like it belongs to your uncle the con man, Crooked Larry.
Sector 659, our estimated time of arrival is 1158.
Bayesian inference creates a rigorous mathematical approach to calculating probabilities based on new information. And it sits at the heart of the Coast Guard's Search and Rescue Optimal Planning System, SAROPS.
He's been missing since 7:30 this morning, so I'm going to go ahead and do a SAROPS drift.
SAROPS takes information about the last known position of the object of the search.
What's the direction of the wind?
Along with the readings of currents and winds, and combines them with information about how objects drift in the water to simulate thousands of possible paths the target may have taken. These get processed into probabilities, indicated by color, and turned into search plans to be executed.
SAROPS is really a workhorse for the Coast Guard. It does a lot of the calculations for us and provides us with a lot of valuable search patterns and search planning options.
I thought he was pretty far offshore, but he said he was okay, so I kept going.
Word of the search has spread. A boater calls in a sighting from earlier in the day.
What I did is I went in and put that information into SAROPS, and it changed everything.
SAROPS quickly recalculates all the probabilities and generates a new search plan. The area has shifted about 3 miles farther out to sea.
We are on scene, commencing search pattern now.
Keep a good lookout.
Roger, coming up.
We're assessing the situation on scene. Any object you see in the water, please take a closer look at. Paddleboarder, port side.
Roger, we have located a paddleboarder with 01 person on board.
I have a visual. All right.
As it turns out, the search has been a drill. Hours earlier, the paddleboard was placed in the water by another Coast Guard ship and allowed to drift. The instruments mounted on it are there to measure wind and record the path it's taken, information that will later be used to tweak the drift simulations in SAROPS. Though the system performed quite well today.
The object was right in the middle of our search patterns. So SAROPS was actually dead on accurate in predicting where we needed to search to find the missing paddleboarder.
To be able to call a family and say your family and friends is coming home is absolutely a call that all of us should have the chance to make. And fortunately, because of stuff like this, we do get to make that call.
The computational complexity of updating probabilities held the Bayesian approach back for most of the 20th century. But today's computing power has unleashed it on the world. It's in everything from your spam filter to the way Google searches work to self-driving cars. Some even find in the Bayesian embrace of probability similarities to how we learn from experience. And they've built it into computers, making it part of a powerful new force, machine learning.
In the past, when we programmed computers, we tended to really write down in excruciating detail a set of rules that would tell the computer what to do in every single contingencies.
But there's another approach, to treat the computer like a child learning to ride a bike. No one teaches a child to ride using a set of rules. There may be some tips, but ultimately it is trial and error, experience, that's the instructor.
The new thing, the new kid on the block is machine learning, specifically something called deep learning. Here, we don't inform the computer through rules, but through examples. So similar to like a small child that falls down and learns from this experience, we just let the computer learn from examples.
Suppose you want to train a computer to recognize.
Okay, so this last topic that I show you, Bayesian probability, is one of my favorite. And the machine learning that they are talking about uses Bayesian approach also. Okay, well, I hope you like this video and now you have a better understanding of statistical, mathematical, and computational analysis and how useful they are in a real life. Also, I hope you are interested to watch the whole video on NOVA because I just showed you some parts of this video. I hope actually I can cover all of these interesting concepts this semester and you can find them useful also. Okay, we'll see you later. Take care of yourself.